Okay, greetings to all of you. I'm Surendra. So, in the last video, we have discussed the semiconductor physics fundamentals and we have covered the essential concepts. Okay, so now let's directly jump into problem solving. Let's start with the very first question given in the textbook. So, it says the intrinsic carrier concentration of germanium is expressed with this equation whose band gap energy is given 0.6 electron volt. So basically, we need to calculate number of electrons available at 300 Kelvin and 600 Kelvin, and we need to compare the results with that of the silicon. So to solve that, first let's start with the silicon calculation. For silicon, the number of free electrons in intrinsic state is given as 5.2 into 10 power 15 into 3 t power 3 by 2 into exponential of minus Eg by 2 kT electrons per cubic centimeter. So at 300 Kelvin, Ni is 5.2 into 300 power 3 by 2 into 10 power 15 into exponential of minus 1.12 into 1.6 into 10 power minus 19 by 2 into 1.38 into 10 power minus 23. This is joule per Kelvin and 300 Kelvin. Okay, now let's plug these values into our calculator and find the result. 10 power 15 into 300 power 1.5 into e power minus 1.12 into 1.6 10 power minus 19 by 2 into 1.38 into 10 power minus 23 into 300. So that will be 1.077 into 10 power 10 electron per centimeter cube. At 600 Kelvin, we need to change the temperature from 300 to 600. Yeah, it is 1.526 into 10 power 15 electron per centimeter cube. Okay. Now let's calculate for germanium. For germanium, it is 1.66. In the equation, it's 1.66. I'll write that. Ni is equals to 1.66 into 10 power 15 into t power 3 by 2 into exponential of minus Eg 2 kT by t. Note that the Eg is different here. It is 0.66 electron volt. So at 300 Kelvin, we need to change 5.2 to 1.66 and the temperature from 600 to 300 and Eg to 0.66 from 1.12. So Ni will be 2.494 into 10 power 13 electron per cubic centimeter. At 600 Kelvin, now we need to change the temperature from 300 to 600. It's 4.1487 into 10 power 16 electron per cubic centimeter. Okay. So now the comparison is at 300 Kelvin, germanium has more number of electrons per cubic centimeter than that of silicon at 300 Kelvin. Similarly, at 600 Kelvin, germanium has more number of free electrons than that of silicon. Okay, we have done part A. Now let's see part B. So part B says determine the electron and hole concentration if germanium is doped with phosphorus atom at a density of 5 into 10 power 16. Okay, so basically phosphorus is a donor atom. It has an extra free electron. So the majority of charge carriers will be electrons. So number of electrons will be Nd. That is equals to doped density of concentration. It is 5 into 10 power 16 centimeter power minus 3. Now Np is given as Ni square by Nd. You must remember that NP times Ne is equals to Na square. So if N is Nt, then Np is equals to Na square by Nt. That is equals to, this is Ni for germanium at 300 Kelvin. Let's say we are doing it for 300 Kelvin for germanium. It is 2.494 into 10 power 13 whole square by 5 into 10 power 16. Let's plug those values in our calculator. 2.494 into 10 power 13 whole square by 5 into 10 power 16. It is 1.24 into 10 power 10. Okay, charge carriers per cubic centimeter. At 600 Kelvin, Np is equals to, we need to put Ni square for 600 Kelvin. Okay, we just need to change 10 power 13 to 10 power 16, and this is 4.1487. It is 3.44 into 10 power 16 charge carriers per centimeter cube. Okay, so the first one is done. Now let's go to the second question. So the second question says an n-type piece of silicon experiences an electric field. They gave electric field. We need to calculate the velocity of electrons and holes. Okay, we know that velocity is directly proportional to electric field. So that is equals to mu e. So velocity of electrons equals to mobility of electrons times electric field. Mobility of electrons is given by 1350 centimeter square per volt second. Electric field is given as 0.1 volt per micrometer. Okay, so volt and volt is cancelled. We need to plug these values in our calculator. 1350 into 0.1. Let's say we will get velocity in centimeter per second. 1 meter is 100 centimeters, and there's a micro 10 power minus 6. So this is 1.35 into 10 power 6 centimeter per second. Velocity of holes is given by mobility of holes times electric field. That is equals to, usually if we use this vectors, this will be negative, and this is positive. This will be 480 centimeter square per volt second into 0.1 volt per micrometer. We just need to change 1350 to 480. So it's 4.8 into 10 power 1, 2, 3, 4, 5, 10 power 5 centimeter per second. Okay, this is part A. Now let's see part B. It says what doping level of electrons is necessary to provide a current density of 1 meter per micrometer square. Assume whole current is negligible. Okay. It says whole current is negligible. That means NP is equals to 0. So we have only Ne. We know that current density equation is mu E N Q. Current density is given as 1 milliampere by micrometer square. Mobility of electrons is 1350 centimeter square per volt second. Electric field is 0.1 volt per micrometer. We need to find N. Charge carrier is 1.6 into 10 power minus 19 coulomb. Coulomb per second is ampere. 1 meter can be cancelled. So volt will be cancelled. Yeah. Rearranging this equation, N is equals to 10 power minus 3 by 10 power minus 6 into, this is 100, 1 meter is 100 centimeters, and we have 0.1, sorry, micro can also be cancelled, so this won't be there, and into 1350 into 1.6 into 10 power minus 19 centimeter power minus 3. So the doping level of electrons is given as 10 power minus 3, 100 into 0.1 into 1350 into 1.6 into 10 power minus 19. It's 4.629 into 10 power 11 centimeter power minus 3. Okay. So yeah, this is how we need to use our fundamentals in solving our problems. So in the upcoming videos, we'll be solving more and more problems. So stay tuned to the series. Thank you. Bye. We'll meet in the next video.